All right, let's dive in. Today, we're going to crack the code of gases. You know, they're everywhere, all around us, but what is really going on with all those tiny particles? Let's find out. You've probably seen this, right? You walk out on a really cold morning and your car tire looks kind of flat. But then you start driving and a few minutes later, it looks totally fine. That's not magic, that's physics. And it's the perfect clue to understanding the secret life of gases. So for the longest time, scientists were pretty good at describing what gases do. They figured out all these rules, these laws that could predict exactly how a gas's pressure and its volume and its temperature are all connected. But, knowing the rules of a game is one thing. Understanding why the rules are the way they are is a whole different story. And that's what they had, a really fascinating puzzle. All these different observations were like scattered puzzle pieces. The question was, how do they all fit together to show us the big picture? I mean, the patterns they saw were just incredibly consistent. They did experiment after experiment and came up with laws like Boyle's law, pressure and volume, and Charles's law for volume and temperature. These are what we call empirical laws, which just means they're based purely on what you can see and measure, and they work perfectly for describing things on a big macroscopic scale. But here's the catch. Those laws are fantastic for predicting what's going to happen, but they don't tell you a thing about the microscopic dance of molecules that's actually causing it all. It's like they describe the shadow perfectly, but they don't tell you anything about the object that's casting it. To get to the why, we needed a whole new way of thinking. And that brings us to the solution. It's a beautifully simple model called the kinetic-molecular theory. So let's break down the 5 big ideas that it's built on. So, it's called the Kinetic-Molecular theory, or just KMT for short. Now, that sounds like a mouthful, I know, but the idea itself is actually brilliant. It basically says, hey, what if gases are just a bunch of tiny, fast-moving particles? If we figure out the basic rules for how they move, maybe we can explain all those complicated gas laws. And it all boils down to these 5 core assumptions, or postulates. First up, gas particles are always moving, all the time, in random, straight lines until they hit something. Second, the particles themselves are super, super tiny, so small that most of a gas is actually just empty space. Third, what we feel as pressure, that's just these particles constantly crashing into the walls of their container. Fourth, the collisions are perfectly elastic. Think of them like super bouncy billiard balls that never lose any energy when they hit each other or the walls. And finally, and this one is the absolute key, the temperature of a gas is nothing more than a measure of the average kinetic energy of its particles. Okay, so those are the rules of the game. Now, for the really fun part, let's put this theory to the test and see if it can actually solve that gas law puzzle we started with. Remember Boyle's law? If you take a gas and you squeeze it into a smaller box, but you keep the temperature the same, the pressure goes way up. We've all seen this happen, right? But KMT is what tells us why. And the logic here is just so cool. Think about it. You shrink the container. Those little molecules are still zipping around at the same speed, but now they have way less room to move. They're going to hit a wall much, much more often. More collisions per second means, you guessed it, higher pressure. See, it just makes sense. Okay, let's try another one. Montaine's law. This one says if you heat up a gas in a sealed rigid container, its pressure is going to go up. This is exactly why you never, ever throw an aerosol can into a fire. So how does our theory explain this? Yeah, it all circles back to that 5th big idea. Higher temperature means higher average kinetic energy, and that means the molecules are moving faster. So now they're not only slamming into the walls way more often, they're also hitting with more force every single time. And that 1-2 punch of more frequent, more powerful collisions is what we measure as a big increase in pressure. So this link between temperature and speed, it's everything. But we need to dig just a little deeper here. Because it turns out it's not quite as simple as just one average speed. See, I keep saying average for a reason, because in any sample of gas, you have this huge range of speeds. You've got some molecules that are basically race cars, moving incredibly fast. You've got others that are just kind of plodding along, and most are somewhere in the middle. It's a whole distribution of speeds, not just one. And of course, scientists have a name for this. It's called the Maxwell-Boltzmann distribution. It's basically a graph that gives us a snapshot of the gas, showing us how many molecules are moving at every possible speed. It's the complete picture.
So when we talk about heating a gas, what we're really doing is changing the shape of that whole distribution. As you can see right here, if you take some nitrogen gas and you heat it up, that average speed for all the molecules shoots way up. So really, what's going on under the hood is that the entire range of speeds gets a boost. When the gas gets hotter, you get way more particles zipping around at those high speeds, and far fewer that are just poking along at the low speeds. The whole crowd just gets more energetic.
All right, one last piece of this puzzle, and it's a really cool one. We've talked about how temperature affects speed, but what about the actual mass of the molecules themselves? Okay, get this. This is the key. If you have two completely different gases, say helium and nitrogen, but they're at the exact same temperature, their molecules will have the exact same average kinetic energy. It doesn't matter what gas it is. It's a fundamental rule. Now just think about what that means for a second. Kinetic energy is all about mass and speed. So if the average kinetic energy has to be the same for both a tiny little helium atom and a much heavier nitrogen molecule, well, how does that work? The only way the universe makes that happen is if the lighter helium atom moves on average way, way faster to make up for its smaller mass.
And this isn't just theory. You see this in real life. It's exactly why a helium balloon deflates so much faster than a regular air-filled one. Those tiny, super fast helium atoms are moving so quickly that they can literally find and escape through the microscopic holes in the balloon. It's a direct result of them being so lightweight. All right, so let's wrap this up. What are the big takeaways? First, gases are just tiny particles that are constantly and randomly moving. Second, a few simple rules about that motion, the KMT, can explain all those complex gas laws we see. Third, temperature is just our way of measuring the average kinetic energy of those particles. And finally, at the same temperature, lighter molecules will always move faster.
Now, this whole theory is incredibly powerful. It works perfectly for what we call ideal gases. But what happens when you have extreme pressures or super low temperatures? What happens when those little assumptions we made about the particles having no volume or not attracting each other start to break down? What happens when gases stop being so ideal and start getting real? Well, that's a story for another day.